Okay, let's talk about Zener diodes. What I want to do is walk you through how to use a Zener diode, do the math, and explain kind of how it works in a circuit. Okay, so example, we have to use a motor. So essentially there's a small motor here, and the motor itself requires 6 volts to run in the way that you want it to run. It's designed to run on 6 volts. It also is a pretty small motor, like maybe a haptic motor or something. So it only draws at, let's say, 42 milliamps. So Zener diodes are good for loads that are small, like under an amp, but if you go for higher loads, there are other ways to stabilize the voltage into a load, but in this case, we're going to just use a Zener diode to stabilize the voltage across this. Now, if I wanted to do that, I could just have a resistor here, and I could choose that resistor so that it had a 6 volt drop as well, and then I'd have 6 here and 6 here and 12, and it would work out. But the problem is, this motor, as it's under load, it will change its resistive nature. When it does that, it'll have a different voltage drop. There'll be a different voltage drop here. They're gonna change the way they divide up this 12. It is not gonna work for you. So what we do is we want really stable 6 volts for that motor. So we're gonna put a diode in here, and it'll be a Zener diode. So you'll see I'm drawing this actually a little upside down. So regularly, if I wanted a diode to have current going through it, I would draw it down. Right now I'm going to draw a standard diode, and then I'm going to put these little wings on it. Now I have a Zener diode. Special thing about a Zener diode, it has a specific reverse breakdown voltage. And that voltage is set to a certain amount, and specifically a Zener diode can work in that range. Like a regular diode, if I had a breakdown voltage of say 80 volts, if I pushed it to 80 volts, if I gave it an opposite voltage of 80 volts and it went past that, it would fry the diode. It would just say, nope, not working anymore. But in this case, a Zener diode is designed specifically to work beyond its breakdown voltage. So let's just say we're gonna get a diode, we're gonna go and choose one, and the voltage, the Zener voltage on that, which is the reverse breakdown voltage, is gonna be 6 volts. So I have a 6 volt diode. It's designed specifically to run in reverse at 6 volts, no problem. All of a sudden, I've got this guy in 6 volts, and this guy, because it's in parallel, is gonna have 6 volts as well. Now, I've got this regulator, this 6 volts, these guys are in parallel, and I know that this guy is gonna have a voltage drop of 6 volts. It's just Kirchhoff's law. If the voltage drop across this leg is 6 volts, then that's gonna be 6 volts. So I know my VR is gonna be 6 volts, no problem. Now, to make this work, to make this circuit work, this resistor, it doesn't matter, I guess, what it is. If it is working, that's going to be 6 volts because that's 6 volts. But if that's the wrong resistor, this isn't going to be 6 volts. It'll be some other number, and I'll show you why. It's about the current. If we look at this circuit, we know that this guy needs 42 milliamps. The way the Zener diode is going to work, actually, is it's going to allow a certain amount of current to run through here. And if that current that's going through here is more than 42 milliamps, it's going to allow some of the current to go here. And that's actually how it manages the voltage. So what we're going to take a look at is what value we're going to put here so that I have at least 42 milliamps going through there. So we want to go more. Let's roll for 60. Okay, so I know that the current that I want to go through here is 60 milliamps, and more specifically, that's going to be IR. So now I have to choose my resistor. So I know that R is going to be V over I. I'm just pulling Ohm's law out of my pocket, and I'm going to say, okay, wait a second. I know that, and I know that as well. So I'm going to say that's 6 volts. So for this thing to work properly, this will have a 6 volt drop. And I know that I need more than 42, so I'm just shooting for 60. So if I put 60 milliamps in here, 0.06 amps, that is going to be 1,000 ohms. If I put a 1,000 ohm resistor there, then I'm good. I now have 60 milliamps going through here. I'm going to have 42 going through here because it's more than 60, and this guy is going to be dropping 18. 18 milliamps are going to be going through here. So I could make this a little smaller or a little bigger, but I'm going to go for 1,000 because I got one on my kit. It's a good number. You can also look at this another way, where you can actually say, if I had 1,000 here, and I had a 6 here, and I put some other device there, would it run? So for instance, I could actually say, I have an eraser somewhere, here it is. I could say that I didn't know what was going on here. Let's say I had a load, like a light bulb or something that I wanted to run with this circuit, or I had a 6-volt Zener diode and I had a 1,000 ohm resistor and I had already this hooked up already. So, and I had, let's say, a light here. If I want that light to run on 6 volts, then I've got to think about how much current it's going to draw. So I'll do the math for that. And essentially, that's just going to be this. I and light, the current for the light is going to be the voltage over the resistance of the light. Now, I don't know the resistance, but what I'm going to do really, because you know that if you measure the cold resistance of a lamp, you're in trouble, because as soon as you turn it on, the resistance completely changes, it gets higher. So best bet is to actually put an ammeter in there. Anywhere, just go up to your DC power supply, run that light on 6 volts, and find out how much current it needs to run at 6 volts. Now, this resistance is going to change, so I can't measure that resistance when it's on, so that formula is actually not going to help me. I'm just going to measure it. Light measured, I'm just making that up, but I'm putting an M there because that's the measured value, is going to be 52 milliamps. It's going to be 52 milliamps. So, you know, that's a little tight. It's a little closer to this. It's good to go maybe a little higher. So actually you might put an 800 in here, because if you did, if you put an 800 in here, you'd have more current going through. And again, just to recalculate that, let's say I had this at 52 and I wanted to put an 800 in there. What I'm going to do is I'm going to say, I want to find the current going through there if I did put an 800 there. So I'm saying, hey, I want this light to work. It needs 52. I know I got 1,000 and it's going to give me 60. I want a little bit more. So what happens if I throw an 800 in there? So I'm going to say IR, well, that is V over R. Now, this voltage drop, what is it? Well, I know what my R is going to be. It's 800 ohms. What's the voltage? Well, just use Kirchhoff's voltage law. I have 12. If it's working, I'm going to drop another 6. So the voltage drop is going to be 6. So I'm going to go for 6 volts here, and that is going to be, what is that? What is that anyway? So let me just put this here. That's 6. 6 divided by 8 is 3 over 4. So that's 75. So that's 75 milliamps. So I got 75 milliamps. So we're good. So absolutely, that's got 75 down there. I need 52 because I measured it. So I'm good. That's how we use Zener diodes, and the math is actually pretty simple. So if anything, I'm going to throw something at you in like a test or a quiz or something where this value is going to be not quite enough. The value here, the resistance, pardon me, is going to be too high, and you're going to get maybe 50 milliamps here, and you need 52, and it's not going to work. Other than that, I'll just give you a circuit that does work, or maybe I'll ask you to design a circuit and choose the resistor. It's pretty simple. Zener diodes. That's it.